Okay, today we will discuss lesson 2.2, the measures of variation. So if you recall, we already discussed the different measures of location, the mean, median, and the mode. This time we will discuss the different measures of variation. When we talk about variation, we wanted to look into how the data vary from each other. Okay, that's the concept, or whether the data is dispersed or not dispersed. Range, average deviation, and variance are some measures of variation. Skewness, kurtosis, it also explains the variation of our data set. Okay, so we will discuss three measures of variation: the range, the average deviation, and the variance. For the average deviation, we will use average deviation based on the median because variance is already based from the mean. We have here the different formula. You can see it in the presentation. In calculating the range given on group data, we have the highest value minus the lowest value. In the group data, we consider the upper limit of the last class interval and then the lower limit of the first class interval plus a constant one. For the average deviation based on the median, it's simply the sum of the absolute deviation from the median divided by n. Okay, for group data or data in a frequency distribution, we simply get the product of your frequency and the absolute deviation between the class mark and its median all over n. N is also the sum of the frequency. Okay, whereas the variance we have here, we call it the computational formula. This computational formula is basically derived from its definitional formula. So variance is equal to n times the sum of x sub I square, I from 1 to n, minus the sum of x sub I from 1 to n, quantity square, divided by n times n minus 1. Okay, for group data, we have here n times the sum of the product of f sub I, x sub I square. X is our class mark minus the sum of the product of frequency and its class mark, quantity raised to 2 all over n times n minus 1. The standard deviation is simply the square root of our variance. Okay, we calculate also the standard deviation as a measure of variation data. In the interpretation, we normally use the standard deviation. Standard deviation is simply the square root of the variance. Why do we need to use the standard deviation in the interpretation? Simply because during the computation of the variance, we all square the units. Meter, and if you calculate for the variance, the unit meter basically becomes meter square. So that is why to interpret or to have a better interpretation, we must get the square root of the variance, which is the standard deviation, to go back to your original unit. So this time, we will discuss first the range as a measure of variation. Let's talk about the properties of the range. First, we have here range is easy to calculate and easy to understand. Second, range tells us nothing about the dispersion of the data that fall between the two extremes or two extreme values. Say for example, we have here two sets. So given that they have the same highest value and lowest value, take note that they will yield the same value of the range. But if you look at the data, it is obvious that set B is more dispersed or more varied than set A. So that is why it tells us nothing, but it tells us nothing about the dispersion of the data that fall between two extreme values. Third is range can be an adequate measure of variation when the sample size is quite small. Set A. So we calculate the range or we describe variation using the range. So take note that your range is simply the highest value minus the lowest value. Okay? So our highest value, let us go back to our data. Our highest value is 15 and the lowest is 3. We have here 15 minus 3. Okay? So our range therefore is 12. Okay? So we describe the value 12 as, okay, set A vary by about 12, or the variation of set A is about 12 using the range. Okay, let us try to solve the range given group data. Let us go back to our example. I mean formula rather. Okay. So range is equal to the upper limit of the highest class interval minus the lower limit of the lowest class interval plus the constant one. So let us erase this. We have it here, the upper limit, the lower limit plus 1. Okay, so go back to our example. This is the highest class interval. Okay, and the upper limit is 20. So we write here 20 minus, this is our lowest interval and the lower limit is 1. So we write 1 plus 1. Therefore, our range is simply 20. Okay? So to interpret, the scores of the students in a particular test vary by about 20 using the range. Okay? Now we will discuss another measure, which is the average deviation. Okay, so we have here two properties of average deviation. First is that the sum of the absolute deviation from the median will always be less than the sum of the absolute deviation from the mean. So I have mentioned earlier that there is an absolute deviation from the mean. However, for the purpose of our discussion, we will only include average deviation from the median. Okay, as I've said, it is because the variance is already a deviation from its mean. Okay, the second property is that the main drawback of the average deviation is that due to the absolute values, it does not lend itself readily to further mathematical treatment. Okay, so we will use this example to solve for the average deviation based on the median. Okay, so we calculate first the median, since we need the median value to calculate for the absolute deviation. So let's start with the median. Okay, if you can recall, to determine the median value of a raw data or ungroup data, we must arrange first the data. Okay, either lowest to highest or highest to lowest. Okay, it doesn't matter because its middle value remains the same. Okay, so we have here 1, 2, 3, 4, 5, 6, 7, 8, 9. So since n is 9 and it is odd number, okay, recall the formula of median value given that n is odd. That is simply x sub n plus 1 divided by 2. Okay? So we have here x sub 9 plus 1 divided by 2. So that is x sub 10 over 2, which is x sub 5. We will delete this one. We already know that n is 9. So we have here x sub 10 divided by 2. So we have here x sub 5. Okay? So what is arranged? Okay, it is already arranged. We will look into the fifth. 1, 2, 3, 4, 5. So it is 8. So our median is 8. We will now get we will now write the given x sub i's, and then we subtract it with 8. Why? Because 8 is our median value. Okay, so we have 3, 4, 5, 6, 8, 3, 4. Okay, so 3 minus 8 is 5. We will not use negative 5 because we are getting the absolute difference. So we have here 4. We have here 3. We have here 2, 0, 1, 2. We have 4. And we have 7. Okay, so let's have here another space. Take note that average deviation is equal to so we will use AD to denote average deviation. Okay, we have the formula absolute difference from the median divided by the n. Okay, sorry for that. Okay, so we will add this column here. So we have here 9, then we have 5, so we have 15, 9 plus 5, 14, 15, 16, 17, 18, 19, 20, 21, plus 7, so we have 28. Divided by, take note, n is the total of observations, and we have 9. Okay, so we divide 28 with 9. The average deviation based from the median is 3.11, approximately 3.11. Okay, so how do we interpret it? So we go back to our original data set. So we say that the variation of set A is about 3.11. This is 3.11 using the average deviation based from the median. Okay, this time we will solve the average deviation given group data. Recall the formula we have here. Average deviation is equal to the sum of the product of its frequency and the absolute deviation from its median divided by n. So we will add another column here for our class mark. Okay, so we already know the class marks for these intervals as discussed in the previous video lecture. We have 3 for the interval 1 to 5, then 8 for 6 to 10, then we have 13 and 18. Okay, so calculating the average deviation given group data. In the median, we have to solve first for its median. Okay, recall the formula of the median. We have the lower class boundary of the median class, its class size. We have here n over 2 minus the less than cumulative frequency. One step lower of the median class and the frequency. Okay, to determine for the median class, we have to divide n by 2. Okay, so our n is 20 divided by 2, we have 10. So we determine 10 using the cumulative frequency. So we will solve first for the less than cumulative frequency. Okay, here we have 3, 8, 18, and 20. So this is now the median class. So we will take note of this class interval. Okay, so we go back to our formula. We need to know its lower class boundary. The lower limit is 11. So the lower class boundary is 10.5. And the class size is 5. So we simply add it with our class size. But before you add class size with 10.5, we have to multiply it with this. Okay, so we have here 10. Then the less than cumulative frequency, one step lower. This is the median class. This is one step lower. Its less than cumulative frequency is 8. So we have to write it here 8. Okay, and we need to also include the frequency, which is 10. Okay, so we have here the median value, 11.5. Okay, so take note of that. We will write it here. We will use that one in calculating the average deviation. So we have here 11.5. Median is 11.5. Okay, we will add another column for class mark minus the median. Okay, so that is 3 minus 11.5, 8.5. Take note that this should be absolute value. Meaning we do not expect a negative answer here for its difference. Then we have here 8 minus 11.5. So we have 3.5. Then 13 minus 11.5. So we have 1.5. And then 18 minus 11.5. So that's 6.5. Okay. And then adding another column. Okay. We have to multiply the deviation with its frequency. So multiply this with the frequency. Okay, so that is 3 times 8.5. So we have 25.5. Then 5 times 3.5. So that is 17.5. Okay, then 10 times 1.5. So that is 15. Then 2 times 6.5. So that is 30. Okay, then after that one, we need to add. Okay, we need to know the sum of this column in order to substitute it with our formula. So simply add 25.5, 17.5, 15, and 13. So we get 71. We will substitute that one here. Okay, so our average deviation will be equal to 71, which is the total or the sum of this column, and we divide it with the total frequency, which is 20. Okay, so our average deviation is equal to 71 divided by 20, which is 3.55. Okay, so how do we interpret 3.55? So we describe the scores, the variation of the scores of the students in a particular test to be vary by about 3.55 or about 4 points using the average deviation based from the median. Okay, so we move on to the other measure, which is the variance. So we have here properties of the variance. First, variance can never be negative because if you notice that in the formula, all observations here are being squared, so it is impossible for us to get a negative value for its variance. Okay, then the second property is that if each observation of a set of data is transformed to a new set by adding or subtracting of a constant c, the variance of the original set of data is the same as the variance of the new set. Let's take this example, 1, 2, 3, 4, 5. This is our original set. We have set O, 1, 2, 3, 4, 5. Okay. And let's say we have here new set. Let's say we add the original set with a constant value, which is 5. Okay, so this becomes 6, 7, 8, 9, and 10. Okay, so according to the property of the variance, if you will add or subtract with a constant value, the variance remains the same as the variance of the original set. Again, the variance of the new set remains the same as the variance of the original set. Okay, so we will compute now the variance given and group data. Recall the formula, we have it here. Okay, so we will copy that one. I'll put it here. Okay, so this is the formula. So we have the sum of x squared times n minus sum of x quantity raised to 2. Okay, our n is 5. We multiply it with the square of each values. So let us first calculate the variance of the original set. So we have here 1. Sorry. Okay, so we have 1 square, 2 square, 3 square, 4 square, and 5 square. Okay, then we continue here. We have minus. We get the sum 1, 2, 3, 4, and 5. Then we square. Okay, we divide it with 5 times 5 minus 1. Okay, let us solve for this one first. Okay, this one here is 275. So we will solve this. Okay, so the square of the sum of set O, or the observations in set O, is 225. Then we divide it with 20. From here, 5 times 4 is 20. Okay, so therefore, the variance is for set O, or the original set, is 2.5. Okay, so take note that we expect the variance of this set n to be also equal to 2.5. Okay, so we will write it here. S squared for set O, or the original set, is 2.5. Okay, this time we will solve the variance for set n. Okay, so we have here 6 squared. Here 6 plus 7 plus 8 plus 9 plus 10. Okay, then solve. Okay, the resulting value for this product is 1650. So we'll write 1650. Okay, then we subtract it with the sum, the square of the sum of the data set. Okay, so we have 1600. Okay, we divide it with 20, so we have 2.5. Okay, so we have proven that if our original data set is added with a constant value, the variance of that new data set is the same as the variance of the original set. Okay, we move on to our third property of the variance. Our property, it says that if a set of data is transformed to a new set by multiplying or dividing each observation by a constant value c, the variance of the new set is equal to the original variance times or multiplied by or divided by a constant c times a constant value 2. So given that we have still the same observations or data set, and then we have here a constant c, which is 2. Our c is 2, constant c is 2, and we will multiply original set with a constant value, which is 2, in order to arrive with a new set. Let's put it set B. So we have here 2, 4, 6, 8, 10. We expect the variance for set B to be twice of the variance of the original set, since we multiply the values with a constant value 2. Okay, so applying the formula, S squared, so B will be equal to 5, because we have 5 observation. Then we square each. Okay, so we have 2 square plus 4 square plus 6 square plus 8 square plus 10 square. Then we subtract it with the square of the sum. So we add them first before getting its square. Okay, then we divide with still 20. N times n minus 1, so 5 times 4. Here, 1,100. I forgot to square this. Okay, minus. Okay, we divide it with 20. Okay, so the resulting variance for the new set B, is equal to 10. Okay, recall if the variance of the original data set is 2.5, okay, then we multiply it with twice of your constant C. Okay, so we expect our variance for set B, S squared sub B, be equal to 2.5 times twice of your constant C. Okay, so our constant is 2. We'll put it down. So we expect it to be 2.5 times 2 with 2. So basically that is 2.5 times 4, which is equal to 10. Okay, so we have proven our third property of the variance.